Structural engineering is the profession of designing and analyzing structures in order to discern how they can best support the loads that they'll be exposed to throughout their lifetime. There are three main loads that are focused on for this assignment, which are dead loads, live loads, and wind loads. These loads all act upon structures in different ways depending on the angle and magnitude, with the various connections used within the construction industry. This assignment delves into the design of different elements within a domestic shed whilst complying with the parameters of the Australian codes and regulations. The elements that were designed for the purlins, rafters, bracings, and columns, and have been based upon drawings given in the assignment handout. This presentation shall be separated into two parts, Part 1, which was the initial submission, and Part 2, which is the final half of this report. Dead loads are forces that are permanent burdens on the structure. The loads that were considered for the first half of the assignment were the roof sheeting, the purlins or in self-weight, the fibrous plaster ceiling, the insulation, and the surfaces. The roof sheeting and purlin self-weight were calculated from their mass values given in the design tables, while the ceiling and insulation load factors were found in the AS 1170.1. The surface value was one given by El Sayed that he has learned from personal experiences. Combining these values together gave us the total dead loads that need to be considered for this initial stage. The total G value was 0.866 kilonewtons per meter. Dead The next lot of loads that are calculated are the live loads. Live loads are forces that are not permanent on the structure but need to be considered for, such as the load of someone performing maintenance on the roof. Live loads were sourced from a table in the AS 1170.1, but are given in a kilonewton per meter square value, which was then converted to a kilonewton per meter. The table value that we found was 0.34 kilonewtons per meter, which was then converted to the final Q value of 0.476 kilonewtons per meter. The next lot of The last force to be considered is the wind load. The first step of calculating the wind loads is to discern how a number of variables to discover what wind class our project will fall in. The variables themselves were given in the assignment handouts but will otherwise need to be ascertained for ourselves. Our wind region for this project was A. This is the lowest wind speed of the four regions, and this is a non-cyclonic region. Our terrain category was 3. This means there are enormously close space of structures close by that will afford some protection in regards to the wind. The next factor was the shielding class. This relates to how the wind speed is affected by obstruction with similar size to the structure. Our shed was partially shielded, meaning there are at least 2.5 houses per hectare around the shed. The final value was a topographic class, which centers around the effect of the wind based on the location of the structure on a hill, ridge, or escarpment. Our class was T3. Using all of these values, we could discover that our wind classification was N3. This was found in the AS 4055.
Pressure and suction must be considered when designing the members, as when wind flows around a building it can produce some very high suction pressures. These occur mainly at the leading edges. In these areas, the cladding has to be firmly fixed to the structure and the roof has to be firmly held down. The flatter the roof, the higher the suction forces are on the roof. Whereas serviceability refers to the conditions other than the building strength that may render the buildings unusable. Serviceability limit state design of structures includes factors such as durability, overall stability, fire resistance, deflection, cracking, and excessive vibration.
Once all these factors were calculated, we could finally move on to our final purlin design. Luckily for us, our assumed purlin from the start has lasted all this way, so no new one was needed to be selected and adjusted for. For the structure, a double continuous lapping method was decided upon. This method involves bolting the two purlins end-to-end via connection plate with no overlap. Our selected purlin was 6 meters long and had an inward capacity of 2.66 kilonewtons per meter and an outward capacity of 3.44 kilonewtons, without the use of sag rods. As the critical loads were 2.36 kilonewtons and 1.32 kilonewtons respectively, our purlin can withstand the proposed loads. Beams, columns, and their connections allow structures to support compressive and tensile loads, but if the structure is to support longitudinal loads, a bracing system is necessary. For the purpose of this assignment, the main force that is relevant to bracing are the wind loads, being pressure and suction. For this section, a new pressure and suction value are calculated that apply to the walls, which originally we just used the roof pressure values before figuring out there was a different value for the walls. After this, a variety of calculations were done to figure out how the wind was going to act on our structure and what forces were going to be carried by what member. In the roof system, to our surprise, the cross bracing actually carried 0 kilonewtons of force, while the struts themselves carried negative 6.75 kilonewtons of force, meaning that in our shed no cross bracing was required in the roof. Our strut member was a square hollow section, and it was chosen because it was the most economic choice. The next stage was to figure out the wall bracing. The purpose of this bracing is to support our horizontal roof trusses.
The next stage in the report was to design the central and end beams. Beams, also known as rafters, are a structural member designed to support a structure's roof and all of its associated loads safely. Beams are typically a horizontal member that characteristically resist the bending moment. The incorrect design of this member can result in several types of failure, such as buckling or yielding. When designing a beam, it is necessary to first calculate the dead load, the live or imposed load, and the wind load. Following the calculations throughout the report, these loads were 2.1 kilonewtons per meter for dead load, 1.5 kilonewtons per meter for the live load, 8.22 kilonewton meters inward, and negative 7.1 kilonewton meters outward for pressure and suction of the wind loads. Beam UB 150 18.0 was chosen for the central rafter and proven safe. The same process was followed with the revised calculations to calculate the end rafters, with the dead load being 1.1 kilonewtons per meter, live load 0.81 kilonewtons per meter, wind load 2.85 kilonewtons per meter inward and negative 4.5 kilonewtons per meter outward. The end beam was chosen 150 UB 14.0 and was proven safe.
Column design. Columns are vertical members which transfer the load of the rafters and fixtures above down to the foundation. The connections designed for are all pin connections. These connections can resist both vertical and horizontal forces, but not a moment, and will allow the structural member to rotate but not to translate in any direction. The dead load and live load for central and end column designs were found in the rafter section. The central column had a dead load of 2.1 kilonewtons per meter and a live load of 3.24 kilonewtons per meter. The end column had a dead load of 1.1 kilonewtons per meter and a live load of 2.52 kilonewtons per meter. Calculations were made to convert these uniformly distributed values for dead load to the values of which each column would be required to bear. These values were 4.2 kilonewtons per meter for the central column and 2.2 kilonewtons per meter for the end column. The wind load was also calculated to find the maximum moment force being 16.2 kilonewtons per meter. These values for the loads were then substituted into an array of load combinations to find the maximum normal force and a maximum moment force with their corresponding normal force. With these values of maximum and corresponding forces, a column was selected and checked for safety for each central and end, both being consistent as 150 UC 23.4. Structural engineers are an integral part of our society. They allow the structures to be designed in a manner that allows them to withstand all the loads and forces they will be exposed to. Throughout the process of writing this assignment, a greater understanding has been garnered of what it means to be a structural engineer. This assignment has exposed the authors to new factors not previously studied, such as wind loads and how they function on structures and what role bracing plays in a structure. Visiting the Mawson Lakes campus also allowed Group 9 to see the type of structure we were designing up close and personal, and to enable a greater comprehension of the members' purposes. The final design of the shed has been completed to the best of Group 9's abilities and has furthered Group 9's understanding of how to design a structure to withstand the forces it is subjected to. While a considerable amount has been learned during the composing of this report, there is still much more to discover.